The idea of simple harmonic oscillators can be extended to other systems. So imagine that we have a wire here and we have some kind of heavy mass on the end of it. And this mass has some moment of inertia. And what I do is I twist the mass some angle theta. Now, what's going to happen is that is twisting all this wire up here. And, well, that's going to be shear, just like before, and so it's gonna be linear with the torque is going to be linear with respect to the amount of twist, and so it's going to be minus kappa, lowercase Greek kappa, times theta. Okay, well, we also know that torque equals I alpha, so we could then say that I alpha equals minus kappa theta. So alpha equals minus kappa over I theta. And so the second derivative of theta with respect to time equals minus kappa over I times theta. Well, you recognize that that's the same differential equation that we had before. So we could then say that theta equals some amplitude cosine omega t, okay? And so that means this thing's going to rotate. When you push it off this way, it's going to go back and forth, back and forth, back and forth. So it's going to be twisting back and forth, twisting back and forth. And so call that a torsional pendulum. There are certain kind of clocks. They go back and forth like that. And so you know that the period is going to be related here. So basically, it's going to be 2 pi over omega. You know that the omega there was going to be the square root of kappa over alpha. So the period is going to be 2 pi square root I over kappa. And so, again, this looks a whole lot like the other simple harmonic oscillator with a mass on a spring. And in fact, it is. It's just basically using different letters, but you get the exact same sort of relationship. So you can just twist something back and forth, and it's going to have the same sort of periods.